Okay, awesome. So I'm gonna quickly, like 1 minute, gonna give background on our company. So we run very high performance LLM inference. We build the software from the actual like intrinsics of the GPU. So if you're on NVIDIA, that would be like PTX. And we build up custom inference engines. We use existing inference engines and to optimize them and make them run as efficiently as possible. We focus on AMD because there's so much to do there, and there's so much value to extract from making this hardware better. There's so much compute scarcity in the world, and people are starting to use AMD now, but we've been experimenting and optimizing AMD for about a year now. When the company started, this was our kind of like the first thing that we were doing, and we've learned a lot along the way. And I'm excited to share some of that. And specifically, what I'm going to share is specific examples where our engineering team has grabbed the out of the box software that comes with AMD and instead rewrites and optimizes, mostly using agents, using coding agents, to make the hardware run as efficiently as possible. And it's very surprising how far you can push it. I guess it's not surprising from the hardware sense, because if you compare the hardware statistics of like an MI355X to a B200, let's say, you'll see that in terms of like petaflops for, let's say, FP4, which is what most inference runs on, MI355 has 10 petaflops of FP4, while NVIDIA B200 has 9 petaflops. I think this is a bit higher for Ultra, for like B300s. But generally, it's very comparable hardware statistics. That's enough of me saying all that. That's kind of like the background on us. Let me talk a bit more about the technical stuff. So yeah, that's me. We don't need to focus too much on that. Okay, so the first thing is what I was talking about before, which is like AMD inference, running AMD inference well is actually a software problem. As I said, the P-flops are comparable. You can, in theory, if you have the same, like in a path of FP4, if you have the same or more number of P-flops that you can support compared to what NVIDIA has, in theory, you should be able to run inference at, let's say, equal throughput, just to normalize out that number. So in terms of HBM, the capacity and the bandwidth is already there. What's missing are sort of like everything after that, which is, okay, can you have a really good runtime so that you can actually run these operations performantly? Can you have these kernels that actually define how you can run code on a GPU as efficiently as possible? And then this all trickles down into your tokens and your, call it TCO per token, call it TCO is total cost of ownership of a GPU. You can call it perf per token. You're like, there's so many terms that people use. Generally, we'll define some terms that will be useful for the conversation. So the general, again, I've already kind of like, I'll go quickly over this one because I've already kind of talked about this, but the stock paths of today, if you just get VLLM running on an MI355 is the latest AMD generation available today. It's comparable to a B200. If you just get the path running today, it really gets you, in general, it gets you much worse performance per token, call it, or TCO per token, than NVIDIA. So there's a lot of work that you need to do on the software stack to actually to have this not be the case, so that you can actually run AMD at equal or better TCO than what NVIDIA can provide. So there's 3 things here. The first one is the generality tax. And this also applies for NVIDIA, which is the kernels that come out of the box for most LLMs are actually pretty general. And there's stuff like page detention, there's stuff that has solved this, but in general, there's a lot of room to improve on just tuning the kernels and writing the kernels that are specific to the dimensions that you care about. The second one is there's a lot of overhead from small operations that are not fused or using parts of memory that you shouldn't be going all the way to. Like sometimes you can go to cache instead of going to call it like HBM, right? So there's a ton of things that you can do on kernel fusion and generally just improving your memory layout. And the third one is when a model gets launched on AMD, normally it doesn't have the same support that NVIDIA has. So you'll see stuff like maybe call it like GLM 5.2, or which is a model that recently came out. GLM 5.2 was immediately supported on Blackwell GPUs, but there was a lot of work that we needed to do, or that the VLLM team did in this case, and the SGLang team too, to actually support the model as fast as they could. But there's still a lag between how fast NVIDIA supports models and how fast AMD supports models, even though AMD is the close like second contender to like day zero support. Because if you analyze all the other chips, the like tail of like Google TPUs, AWS Trainium, they require like months of work. Even like Cerebras, think of Cerebras. Their latest GLM is 4.7, and there's a reason for that. It's really hard for them to support new types of attention, changing from dense to sparse attention, which GLM did with the new GLM 5.2. It's kind of like a tangent, so I won't focus too much on that, but it's still an interesting topic of like how fast can you bring a model to a chip so that you can use it in production. So that you can use it in production. So our solution at Wafer is, what if we just build a completely custom AMD inference layer? And completely custom is kind of fake here. And what I mean by that is we use existing inference engines, we use existing runtimes and sort of fork them to create like better things and support for a broader range of things that we care about. So AMD has an inference engine, which is kind of like the equivalent of, for the people that know NVIDIA's TRT-LLM, but it's called Atom. And Atom is a very new project, but we think it sets a pretty good foundation for what an inference engine on AMD should be. So instead of rebuilding what the Atom team is doing, we fork our own version of Atom and we add stuff on top. So some of the stuff that we add on top is goes all the way from kernels. We write HIP kernels. HIP is the equivalent of CUDA in AMD hardware. So we write HIP kernels to support operations that are not natively supported sometimes to increase the speed. Aider here, mentioned over here, is the equivalent of HIP. Aider is the equivalent of maybe a good equivalent here would be like Qtile or more like QDNN. It's like abstractions that give you easier ways to define like common operations in kernels that are used for LLMs, for MoE, etc. And then ROCm is like the runtime. So it would also, like the analogy in the NVIDIA world would also be CUDA, but CUDA is both used as a language definition and as a runtime definition. So the thing you can do on top, once you like write very custom kernels, the thing you do on top is model-specific decode paths. What this means is like a spec decode path. What this means is basically training a small model to predict the outputs of the big model. It's a common technique used now in basically every frontier LLM, where you have the small model do maybe, let's say, 3 token prediction, and then the big model will just verify the tokens that are that would be the ones that it would have predicted. The reason this is much faster is because verification for an LLM is much cheaper than generation. So this works very well and has been, I'd say this is like a solid 30 to 40% of like the lever you have to pull when optimizing models to like their full potential at the moment. Then the layer on top of that is basically the runtime and cache. I think, as we all know, like context lengths and sort of these like long agent trajectories have become basically the normal thing when you're running agents. Like most people I talk to are running like these coding agents. They're running this like ChatGPT on like this chat that's like 15 or even more, like 25, 50 like prompts in. So you have this huge context and you have this huge pre-fill that you need to fill. And you get to think about like, okay, what are the semantics? What are the strategies that I could use to cache this most efficiently so that I don't have to actually re-input the entire prompt every time a user adds something else. So the concept of like, similar to the concept of a KV cache, where you don't have to go redo the entire key value cache when you're like actually doing the decode in LLM attention. There's also things like prefix caching and other strategies that great projects like VLLM and SGLang do, so that you don't have to re-input your prompt every time you are actually adding stuff on top. And there's a lot of interesting engineering that comes from our team and from many teams around the world on how do you actually optimize the cache to be as efficient and maximally useful as possible. And then on the last layer of that, there's the serving APIs and the load balancing. And this, I would say, is interesting, and it's getting more interesting as more sort of like as you scale, basically. There's like a lot you can do in terms of load balancing. Obviously, it gets very interesting when you have a runtime schedule like Dynamo or Mooncake, where you can actually do prefill disag and have different GPUs do prefill and have different GPUs do decode. And it gets interesting on what type of load balancing you can do, because you can start independently scaling both the GPUs that do prefill and the GPUs that do decode. Whereas before, when you didn't have those separated, you'd have to scale those uniformly. So there is something more interesting here on serving APIs and load balancing in general, but I will say Wafer, for the time being, mostly focuses on the bottom 4 of the stack. And serving API and load balancing are something that we use because we have to have a serving API to serve our tokens. But it's not a massive sort of like focus for us. So now that I've talked about like the general solution here, I want to talk about some like specific optimizations that we've done on models and what exactly we did to achieve what are the like highest speeds on AMD that have been publicly achieved for these models. So for reference, we were the first company in the world to get AMD to #1 on any artificial analysis leaderboard. And this was a great technical achievement by the team, and it took us months of effort to do. But once we did it, we're sort of like trying to increase the speed of the flywheel so that we can keep doing this for AMD hardware, and we can keep increasing the TCO to give people another choice. Our general thesis is like people should not be locked into CUDA just because they were so early to the game, especially with how important AI infrastructure is becoming. So let me talk about this first example. There's actually this is kind of like an overview, and I think I'll skip this because it's more interesting to actually, I won't skip this entirely. I'll just go over it fast, but it's more interesting to actually look at the specific examples and what the exact technical achievements were. But generally, what you could see is that there's 3 levers, or I'll actually talk about the first 2 levers, which are very interesting. The first lever is, can you sweep over the search space of possible configurations in VLLM and SGLang and Atom and TRT-LLM to find, if it was NVIDIA, but on AMD, to find the most optimal configuration? I imagine a lot of you guys have used something like VLLM. And when using this inference engine, you've probably noticed that there's a ton of hyperparameters and flags that you can set. I don't know if you've ever used it on AMD. I assume very few people, compared to the amount of people here that have used VLLM, I assume a very small minority of those people have used it VLLM on AMD or SGLang on AMD. But what you'll see is that to get actual performance, there's like 10x the number of flags that you need to like permute, and finding the best combination of those is a huge permutation problem. So we have a lot of techniques for being really efficient in our search and being really efficient in the way we sort of go over this problem and find the configs that are most optimal. And then once we go to the bottom of that for the kernels, there's a lot that we can do in kernels, and we'll talk about it. But generally, I think these numbers are like not super meaningful because you haven't seen the actual optimization that we do. So I want to just skip over this. I was just talking in general about the strategies that we can do, but now I want to go to the actual like examples. Okay, great. So this is one of our first examples with Atom. So we got Qwen 3.6 to state of the art, and for the graph that you see here, I didn't include the providers, but the common providers like Alibaba Cloud, like Base 10, like Fireworks. I don't know who exactly is on the leaderboard right now, but at the time we took a recording of like what the leaderboard looked like, and we recorded it while blanking out the name of the other providers. But we were able to take the speed of Qwen 3.6 to state of the art by basically doing purely runtime configuration. And this might seem like low-hanging fruit, and in some way it is, but also in another important way, there's so much that you can do by searching this permutation space efficiently. If we had just searched this permutation space naively of like, what are the flags that we need to set in Atom to get this to state of the art, it had taken us like, let's say some absurd number, right? Like, it had taken us like a year or like 10 years to go through like the full like spectrum of choices. But if you build systems that can efficiently use basically AI, ML in some ways, to prune specific parts of the search tree and do this sort of targeted optimization or targeted search where you're going over certain configs that make sense And you can do this very well, and you can do this very well with agents. You can have an agent that benchmarks across the search space and checks if, okay, will this flag make it more efficient? And if I do make it more efficient, what does it mean if I add this other flag in this path? And this is the process that humans would run. But agents are getting so good at autonomous sort of like long horizon tasks and performance engineering that this is actually something that that we were using like every single time a customer comes to us with an inference request. We will run an agent through you to get the absolute max performance we can out of your hardware. And this is something that usually traditional inference providers are not as good at as because they're bottlenecked by humans. So this is kind of like one of our core theses of like, can you use agents to search the space and get to that optimal configuration performance without even having to get into kernel work, which is, it could be very high ROI, but it's also a big sort of like input and much heavier work that takes longer. The second example that I think is probably my favorite by far is when we actually got down to the kernels. So again, in this one, we did include the providers. So it's kind of ironic, but this one was our first result ever where we got #1 on artificial analysis. And this is the one I was mentioning to you guys before, where this was the first time, at least publicly announced, the first time that someone using AMD managed to get a frontier LLM to #1 on artificial analysis in terms of speed. And the way we did this was with this optimization path that I've laid out here. The first one was the config sweep that I talked about, which is basically, can you load in the FP4 weights? Do the kernels exist? If not, you have to write them, but do the kernels exist? Can you quantize the KV cache without losing accuracy? And can you add support for MTP, which is a form of similar to speculative decoding, where you have multiple heads of the model predict different outputs, and then at the end you do verification to decode more efficiently. Then what took us from 260 to 300 was actually writing custom MoE kernels. We did a fusion that fused 6 launches into one, so that there was no intermediate HBM that we had to go all the way to, which managed to speed up the tokens per second from 260 to 300. And then for the last optimization to really get in front of the other providers like Eigen, Nebius, DigitalOcean together, what we did was router fusion plus MoE, so more kernels. And I'll talk more about each one. So one interesting one here is MoE surgery. So MoE is mixture of experts. So what we were thinking about is, how do we remove the empty work? Basically, there's this routing that you do over 512 experts, but generally the mismatch is that these 512 experts give you only about 40 active expert token pairs. What that means is that you can replace replace these separate operations. So you can write one HIP kernel that, instead of doing input output for all of these things and going all the way to HBM, you can fuse all these operations, which are gem, CLU, down gem, reduce, and dequant, into one single fusion, one single big kernel that instead does everything and then returns the result. So instead of going input, output, you can just do input, do every single operation on the GPU, and then output the result. And this was one that was very high ROI optimization. As you can see here, 1.84 faster per mixture of expert call. And this added about 30 to 40 tokens per second end to end. The second one here was another one of the fusions we talked about, where we did the router plus a shared expert. Now, what this meant before is that we used to dispatch the router so that we had the separation between the logits and the shared expert gate up. And these were 2 separate gems. And you can see this illustration here where we're hitting the before as you have the hidden states as 1 gem here times the W router. And then on the other side, you have the hidden states times shared. So these are 2 different mat holes, so which are gems, just generalized matrix multiply. After we did that, we concatenated the weights along N so that we were able to merge this into one single fused gem that actually ended up producing the same exact result. So this was one of like a very creative optimization by one of our engineers that we were very excited about. And to be clear, this only sped up like 10 to 20 tokens per second. But we like to think of performance as just like there are a lot of like performance matters more and more as AI infrastructure becomes bigger and just like permeates every aspect of basically the world, where a 10 to 20 tokens per second increase can mean millions of dollars of saving for a large enterprise because you can run stuff faster, you can finish stuff faster in the GPU. So faster equals cheaper in the GPU world too, because most of the time you're renting or you're buying depreciating hardware that you could be using for something else. The last one I'll talk about is caching the state the model used. And this one's a really sort of like simple one compared to the other ones, which might be a bit more daunting. This one is simply a model like Qwen 3.5 has these full attention layers, and that recurrent hidden state, the recurrent state of the GDN, lives outside the page attention, like the KV cache. So the fix is to build this other cache that's a snapshot of the recurring state. And you also save the KV blocks. And what you'll do is you'll mix both of them and you'll invalidate them together on cache and evictions. So you can keep these states aligned on your cache, so you can have this speed up. Look at these massive speed ups. And this is just a cache trick, right? So this was also something that we did that helped a ton on just thinking about how do you actually save specific parts of memory so that you don't have to go to the expensive memory like HBM, and you can instead hit the most cache as possible. I'll finish up with this and then I'll open up to questions. I don't know if I left a lot of time for questions, but like I'll try to go faster for this one. What we care about at Wafer is, can we close a loop? Can we can we close the loop between what the agent can do and what the human input it needs, so that you can just run these autonomous loops that agents can just search the space for optimizations. The space could be implementing a custom kernel, quantizing specific parts of the model without losing accuracy, training speculative decoding models, smaller models that predict what the big model will output. It could be all the way down to like, if you make this really futuristic and like years down the line, it could be all the way to like, what's the cooling in your data center? What's the power efficiency that you're using from the grid? You could even take it all the way down to like, okay, how should I actually design my chip if I want the maximum performance in this workflow? So I think there's a lot of interesting things to think about in where this model could go, of like, what if you could just give an agent closed loop system where it can search, where it can identify bottlenecks with validity, it can write the kernels, it can write the code to patch it, and then repeat and benchmark that it's actually faster, benchmark that it's numerically correct, and then just go on repeat. And I think this is a very, very powerful thing that even to this day, people are underestimating how powerful this would be. And sort of like, if you take the exponential and the scale. Yeah, so takeaways here, just to finish off, the mode is moving up the stack. There's so much to do in terms of alternative hardware that we want to add compute capacity to the world, and this is a viable way of doing so. MI355 from AMD can be frontier class with the right engineering. Day zero support is still NVIDIA monopoly, still NVIDIA active, but there's something we now have a path to reduce this and to actually make other hardware day zero support native. Custom kernels still represent a big part of the moat of serving inference efficiently. And then agents are a great way to scale this so that you can do this for every model, for every hardware, and in the future have an actual democratized market where we don't have a company that is just 90% of the market like NVIDIA. They make a great chip and we highly respect their engineering, but I just think the world deserves kind of like a choice in like, what chip should I use? And that choice means the world for prices to come down. And eventually what we care about is how do we maximize what we call intelligence per watt? And our focus is building AI that can optimize AI infrastructure. And we think the best opportunity today is with AMD Inference. So yeah, I don't know if I have time, but I'll open it up to questions.
Thank you for a great presentation. Lots of interesting optimization, hardcore engineering that you guys are working on. So kudos to you guys.
Thank you.
Looks like the questions are coming in, but I'm going to start with my question.
Yeah.
The closed loop optimization that you talk about, sounds pretty exciting. Have you thought about even like make that available for both NVIDIA and non-NVIDIA chips?
Yeah. I mean, to be completely frank, we use a lot of NVIDIA chips still, and we do use this closed loop optimization. I think the reason I'm so excited about AMD is I think there's a lot to do with AMD, and NVIDIA already Like if you think about NVIDIA, I think the estimate is like they have like 4,000 CUDA engineers already. So it's
Yeah.
like AMD has like a tenth of that. So it's like 400 ROCm engineers. So it's kind of like the arbitrage and the opportunity that exists in AMD is much higher. So it's much more interesting for us to think about like how much we can help there in terms of like where the delta is. Because the gap from AMD is purely software. As I said, the petaflops is the same. It supports the same. So we do work for both. I think the more exciting thing to think about though is like what happens in a world where you can actually do this for any chip and
Yeah.
make it equally performant as NVIDIA.
Got you. Makes sense. Yeah, certainly it's good to have healthy competition. That will be good for everyone.
Exactly.
I'm all for that. There's a question from the audience, so let me bring that up and then you can take it. Okay. Do you train your own draft models and what method you are using?
Yeah, we do. We do a lot of Eagle. We also do a lot of like normal MTP. But yeah, we generally like I think there's a big part of what I talked about is day zero support. And I think if you don't want to train your own draft models, you should also be okay with waiting like many days or even weeks for like the community to bring one up. Sometimes NVIDIA, AMD, other companies like Snowflake, Red Hat will open source like a draft model and you can just plug that in. But for our customers, we've seen that they really, really care about day zero support. Like, hey, this model just came out. Like when GLM 5.2 came out, our Slack was just like flooded with people being like, oh my God, I'm seeing on Twitter that this is like the best open source model. Can we
Yeah.
host it today? And it wasn't supported on AMD and nobody had released a draft model. So it was kind of like on us to figure out like, okay, we need to go train our own draft model, figure out how to actually like do this so that our customers can use it. So yeah, we do train them. It's pretty fun. It's a pretty interesting challenge overall.
Yeah, I bet. Awesome. Thanks a lot for giving us your time. I'm sure you're busy, have a lot of stuff to do. Appreciate you taking time out and share with us all the interesting stuff that's happening at Wafer.
Yeah, thank you so much. It was great.